Hello and welcome to this video on series parallel circuits. This is a series parallel RLC AC circuit. Some people get scared off by them. I'm going to show you exactly how to solve them. The first thing we're going to do is find and add the series impedances for Z series or ZS, and that's pretty straightforward. Then we're going to do the same for the series part, which I call ZL2C2R, which is inside the parallel part of the circuit. Once we've done that, we can use the reciprocal method to find the parallel impedance in total, which is made up of the resistor and the capacitor and the other series branch we just looked at. And then finally, really easy, add the series impedance to the parallel impedance to get the total circuit impedance, and then we can find the supply current. After we found the supply current, we're going to find the parallel voltage, which I call Vx, you can call it anything, the voltage across the parallel network. And we can do that by subtracting the series voltage from the supply voltage, but this is long-winded and requires subtraction. It's much easier to use polar form and do voltage as current times impedance to find the parallel voltage Vx. After that, we're going to find all the parallel branch currents through R2, through L2, C2 and R, and through C3. And finally, for you, is to find the component voltages shown here. That's your task. Just using multiplication in polar form. It's really easy. The supply voltage is 100 volts at 500 Hz with a period of 2 milliseconds. And the reason that I chose those values is because the voltages and currents are all relatively large compared to each other, so they're easy to see on multi-sim or on any graph that you use. So finding Z series. We'll have a quick look at complex number notation and the angles in between impedances and voltages, or the phases. We visualize our impedances and voltages on the complex plane, but J represents a phase lead of 90 degrees and minus J just means a phase lag of 90 degrees compared to the reference vector. And this shows where inductors, capacitors and resistors live on the complex plane and in phasor diagrams. So find each series impedance and add them together. Resistors have no reactance, so they don't create any phase difference between their voltage and current. So ZR, the impedance of the resistance, is just 1000 ohms, and it's real with no imaginary part. But inductive reactance, XL, measures how much an inductor opposes current through it, and it equals omega L, or 2 pi FL, where L is the inductance in henries. This reactance or impedance is purely imaginary in an ideal inductor, so it has no real part and lives at positive 90 degrees to the x-axis, as in pointing north. Capacitive reactance XC also opposes current and equals 1 over omega C, or 1 over 2 pi FC, where C is the capacitance in farads. And this is purely imaginary in an ideal capacitor, so it has no real part, and it lives at minus 90 degrees to the x-axis, or negative J, or pointing south. Notice that the negative 318 J ohms is equivalent to positive 318 ohms at minus 90 degrees, or pointing south. We know immediately that this is an inductive series network. The inductive reactance and voltage across it will be greater than the capacitive values because the blue arrow is longer than the red arrow. So this is going to be an inductive network. We've got similar triangles for impedance and voltage, all to the same scale. All we do now is add the imaginary parts, and then we add the real parts together. And this gives us Z series in rectangular form, which we can convert to polar form quite easily. Here's ZR, the real part of Z series, and then ZL1, which is positive J, then ZC1, which is negative J, and the sum of the imaginary parts, which I call ZL1 plus the negative ZC1, or ZL1 minus the magnitude of ZC1. The dotted line is the overall imaginary sum, if you like. And we can convert it into polar, this impedance, because it's easier later on for finding impedances, currents and voltages. This shows how we work out the phase angle. The polar hypotenuse length, or modulus, is found with basic Pythagoras, the square root of adjacent squared plus opposite squared, where the adjacent is the real part and the opposite is the two imaginary parts added together to find that dotted line. So rectangular to polar conversion. Consider points A and B on a map. Rectangular form is how cars drive to a destination, and polar form is how aeroplanes fly. And driving a car in polar form isn't recommended. Let's use Pythagoras to find the hypotenuse length, called the polar modulus. The Z series modulus is around 1231 ohms. Now we can find the angle, or the argument. It's tan to the minus 1 of opposite over adjacent, so it's quite easy to do. So our Z series is 1231 roughly ohms at an angle of just over 35 degrees. That's a series impedance done. And this just shows you how to convert between polar and rectangular on a Casio calculator. You need mode 2 for complex mode. So there's Z series rectangular and polar, and what I call poltangular. So the skills we've used is addition, subtraction, basic Pythagoras and inverse tan. Now we found Z series. I chose to find the series branch within the parallel branch called ZL2C2R. It's basically already done because we've got the same imaginary parts because the inductor and capacitor are the same values at the same frequency. The only difference from Z series is the amount of ohmic resistance, the real part. Instead of 1000 ohms, it's 0.1 ohms. So ZR is just 0.1 ohms with no phase difference. So ZL2C2R is really easy. It's 0.1 plus the same imaginary part as we had before. And there it is on the argon diagram. There's our ohm boy ZR and the resultant of the imaginary vectors for the inductor and capacitor, which I call Z imaginary. And polar form will be useful later on for multiplication and division to find currents and voltages. Just change it into polar form from rectangular. Because R is so small, it has really no effect on this impedance. It's almost vertical, this impedance, and is around 718 ohms, so it's almost just an inductor really. There's rectangular and polar for ZL2C2R. There's rectangular, polar, and poltangular. Now to find Z parallel using the reciprocal method like we do with normal resistors. The reciprocal of ohms is Siemens with a capital S, and here's the names of the reciprocals of resistance, reactance and impedance, although their names don't really matter when you're trying to do an assignment. We'll find the reciprocal of each impedance, resistance or reactance, and then we'll add them together, and then we have to find the reciprocal of that to find Z parallel. ZR2 is just the real number, 1000 ohms, so 1 over that is just 1,000th in Siemens, and it's conductance G if you're interested. That's the easy one. The impedance ZL2C2R is shown here, and let's find the reciprocal or the admittance of that. Rectangular division looks long-winded. It's actually easy, but polar division is quicker. I'm going to do it in rectangular form first, just to show you how to do it. We'll find the expected values with a calculator, and then we'll do it on paper to check our answers. Remember to press menu, then 2 for complex mode on your calculator. So 1 divided by 0.1 plus 718.416J. Don't forget the J or I. That's the reciprocal of ZL2C2R. Then we can convert it into polar form as shown. And these are the values that we're going to expect to find. And you'd normally use a calculator, but I'm going to show you the method for doing reciprocals. So we can't have a complex denominator, we have to keep the denominator real. So all we've done is multiplied the quotient by 1. And we're going to change that 1 into the conjugate divided by itself, because anything divided by itself is 1. And it looks difficult, but it really isn't. The conjugate is the same as the denominator, but with a different sign before the imaginary part, that's all. We'll tidy it up a bit, we'll shift this bit over as our numerator. So we've got 0.1 minus 718J divided by the rest. Those two brackets, we just expand them using FOIL, what we call binomial expansion, but it's a lot easier than it looks. So the first two terms is 0.1 times 0.1. The outer terms is 0.1 times negative 718j. Don't forget the j. The inner two terms is 0.1 times positive 718j. And when you add those, they cancel each other out. And finally, we've got the last two terms, which is 718 times minus 718 times j. But remember, j squared is equal to minus 1. So that's minus bracket 718 squared times minus 1. So the last two terms are always going to be the imaginary part times itself, or the imaginary part squared, and it's always going to be real. There's no j part. And it'll always be positive because anything squared is positive. So the reciprocal of ZL2C2R is shown. It's the conjugate, including j, divided by the real part squared added to the imaginary part squared. And that has no j. It's a real number now. I call the denominator Pythagoras because it's like Pythagoras. You square and you add. You just don't square root. And then we split up this fraction into real and imaginary. And then we've got the reciprocal of our impedance, which is what we were after. So that comes out as 1.938 times 10 to the minus 7 minus 1.392 times 10 to the minus 3 J Siemens, which is what we worked out on the calculator earlier. Then we can change this to polar if we want to. It's always good to have both. This is just for your reference with complex numbers, but I've explained it already. So we'll find the reciprocal using polar form. Now this is really easy. This is why it's good to do division with polar form. It's 1 divided by 718. At an angle of 0, take away 89.99. With polar division, it's the amount divided by the amount, and the angle take away the angle. And you can see we've got that right. Now we're going to do C3, find the reciprocal of that impedance. So that's 1 over minus 318.31J. That's the same as 1 over 318 times 1 over minus J. But you might recall that 1 over minus J is just J, and that purple box on the right shows you why, if you needed a reminder. So the reciprocal of the impedance of C3 is 3.142 times 10 to the minus 3J Siemens, and that's a susceptance, which is the reciprocal of a reactance. Let's do the polar form reciprocal of the capacitive impedance. Really easy. 1 divided by 318.31 at an angle of 0, take away minus 90 degrees. So be careful about the double negative. So that comes out as 3.142 times 10 to the minus 3 Siemens at an angle of 90 degrees. Now we're going to add the reciprocals together in rectangular form. And after that, we'll do the reciprocal to find Z parallel. So 1 over ZP is 1 over ZR2 plus 1 over ZL2C2R plus 1 over ZC3. Add the real bits to real, imaginary bits to imaginary, and this is what you have. And that's the admittance, which is the reciprocal of this parallel branch in total. So we flip that upside down, as in find the reciprocal, and then we've got Z parallel. In rectangular form, we use the same method as before, but we'll do it the quick way. The conjugate of the denominator divided by the real part squared plus the imaginary part squared, and we end up with no j because it's a real number. And that comes out as, on the denominator, 4 times 10 to the minus 6 roughly. So ZP is 246, roughly, minus 430 J ohms. And that's our impedance, Z parallel. Convert it to polar if you want to. So that's Z parallel all done and dusted. This just shows you a quick way to find reciprocals using your calculator, which no doubt we will do because it's a lot quicker. Once you've got a rectangular reciprocal, just press Option down and 1 to change it into polar form, and there you go. Now we're going to find Z total by adding the series and parallel impedances together. These are the impedance triangles for Z series and Z parallel. We could add the hypotenuses together on paper at the right angle and find Z total. We could do that, or we're going to do it mathematically instead. So to add, we need rectangular form. Add the real parts to the real parts and the imaginary parts together, and Z total is 1246 plus 287 J ohms in rectangular form. Square them, add them, square root them, gives you the modulus, and tan to the minus 1 of opposite over adjacent gives you the angle of Z total. Now we've got Z total, we can find the total circuit current, and then we can find some voltages later. So current is voltage divided by impedance, just Ohm's law. 100 volts divided by Z total. In polar form, you divide the amounts or moduli and you subtract the angles or arguments. So there's a phasor that we could use. Our supply current is about 78 milliamps. Here, the supply voltage is the reference vector. But we know that the current should be the reference vector in a series circuit because the current is common to R1, L1 and C1. So what we're going to do is spin this phasor diagram anti-clockwise by 13 degrees just so that the supply current is the reference vector. And now supply voltage is at 13 degrees, positive 13 degrees leading the current. So we just need to change the Vs values in rectangular form if we're going to use them. We've got the hypotenuse and the angle from the x-axis for the supply voltage. Cosine gives you the adjacent side, sine gives you the vertical opposite side, so that's where that comes from. 97 plus 22.5 J volts, that should say, per Vs. Much quicker to do it on a calculator in complex mode. Do 100, shift eng for the angle, 13 degrees, and press equals, and it gives you the rectangular supply voltage. Now we can see our waveforms. In green we've got the supply voltage and the current in grey. And as we thought, the supply voltage is leading the current. Down the bottom on multisim shows us 78 roughly milliamps. The time difference between Vs and Is is around 72 microseconds. And we can check whether that gives us the correct phase angle, because the time difference between the peaks divided by the period is the same ratio as the phase difference compared to 360 degrees. So we just rearrange that. The phase difference is 360 times the time difference divided by the period. And the period is 2 milliseconds at 500 Hertz. So the phase difference comes out as 13 degrees, which is what we thought it would be. So we've shown the waveforms are working as we thought they would. Now to find Vx, current times Zp. easy with polar form. The voltage across the parallel branch is the supply current times Z parallel. When you're doing polar multiplication, it's really easy. You just multiply the amounts together and you add the angles, or you multiply the moduli or moduluses and you add the arguments for the technical term. So the voltage X is 38.793 volts at an angle of minus 60.26 degrees compared to the reference vector. So there's the supply current and there's Vx, which is lagging, and it should be lagging by about 60 degrees. And we can prove whether it is on multisim using the same method as before. There's Vx, there's the time difference between the two. So the phase difference comes out as minus 60.4 degrees from observation, which is pretty good. Now we can find the currents because we know the voltage across the parallel branches. Current is voltage over impedance. So the current through R2 is the voltage across it divided by its resistance. So IR2 is 38.793 milliamps at an angle of minus 60.26 degrees. And it's in phase with Vx because current and voltage are always in phase through a resistor. There's IR2's amount or magnitude, and using the formula we used earlier, that shows the phase difference, which is pretty good for observation. Now we can find the current through L2C2R, which is the voltage across it, Vx, divided by its impedance. And the angle is going to be minus 60.26, take away 89.99 degrees. Be careful with the negatives and the positives when you're adding or subtracting the angles. So that's 54 milliamps at an angle of minus 150.25 degrees compared to the supply current, which is the reference vector. You can show that on multisim, and the angle comes out as minus 150.39 degrees, which is pretty close from observation. Finally, the current through the capacitor C3, voltage divided by impedance. Here the angle is minus 60.26, take away minus 90 degrees. So this shows that the current through capacitor 3 is 121 milliamps, but it is leading the supply current by nearly 30 degrees. And we can see it leading there, and from the time difference it shows it as leading by 29.25 degrees, which is pretty accurate compared to our theoretical values. Well, thanks so much for watching. Please like and subscribe, work out the voltages using polar multiplication, and comment with any questions or anything you want to understand better. Thanks so much. It means a lot to me, you watching these, and take care and have a go.